So welcome back to lecture 35. This is part 2. And in this part, before we go any further, we kind of want to do an analogy with the complex numbers. So the textbook goes into this, and it actually might help you kind of keep track of what we're doing. And one of the themes that the author is pointing out in the textbook is that the space of complex numbers and the vector space of all linear operators on a vector space actually have some very similar properties. So some stuff that you can do in the complex numbers has some sort of analog over in the vector space of all linear operators. Right, so in the complex numbers, your basic element is a complex number, right? And that would, you would, the basic object on this side are operators, right? So we have operators over here. On this side, one of the operations you can do is taking the conjugate of a complex number, right? So the conjugate is this guy right here. And the question is, what would be the corresponding operation on the other side? Well, it turns out that we want to think of the adjoint of your operator as being kind of the analog of taking the conjugate. Okay, so if you're thinking, that's one way to think of what the adjoint is. Okay, now we know that in a certain cases, when you take a complex number and it equals its conjugate, that can happen if and only if z is a real number. So somehow we want to kind of identify what are the things that would correspond to real numbers on this side, and those would be the ones that are self-adjoint because they have this property that if we were saying that the operator is equal to its adjoint, right? So that would be saying that the adjoint of t is equal to t itself. Okay, so if we identify the complex numbers with the operators, the conjugate with its adjoint, that kind of tells you that the self-adjoint should really kind of be the things like the real numbers. Okay, and now remember that the length of a complex number, or the norm, right, is equal to the square root of a squared plus b squared. Okay, so that's kind of how we define it. And notice that on this side, right, if this is 1, that's the same thing as saying that z times its conjugate is 1, right? So notice that this is the same thing as doing z times its conjugate squared. Okay, so that would be kind of important going on. But if the length of your complex, or the size, I guess the length of your complex number, or the absolute value of your complex number, is 1. It's the same thing as saying that z composed with its conjugate is 1. So on this side, we know z would correspond to t. The t star would correspond to the adjoint. So over here, what we would expect is that if the length, the vectors that, the complex numbers that whose length correspond to 1 should correspond to isometries, right? Because they have the property that t star t is equal to the identity. Okay, so that's kind of seeing some of the analogy going on over here. And over on this side is we can actually decompose our complex number in the following way, right? We can take the complex number and we can rescale it by its length, and then multiply it by its length. Okay, so this is one way of thinking about breaking up our complex number, right? And one way I'll draw a picture here in a second. This is a different way of writing everything. Okay, because this is the length, right? This is the length of your complex number, and over here, right? This is an element on the unit circle in the complex plane. And over here, you want to think of this as scaling. Right, so we're taking, you can write a vector in the following, you can write a complex number by taking an element that's on the unit circle in the complex plane and then just scale it appropriately. Okay, so let me try to draw a picture of this. there's my unit circle, and maybe I will have my complex number z here. And you can think of this as here is the, if we take this little point right here, that's the complex number z divided by its length. And then what we're doing is we're scaling by the length of this vector. Okay, so that's kind of what's going on in the complex number way. So it's just another way of writing a complex number, right? And we may have talked about this in Math 1B03, where you're kind of scaling a vector, and then you're writing it in terms of cos and sines. But really, what you're doing there is you're picking a point on the unit circle, and then you're scaling it. Okay, so that's kind of why it might be called polar decomposition. And what the polar decomposition theorem that we're kind of aiming towards describing today is that you can do something similar. You can take your z, which would correspond to an operator. You can take this piece right here, right, which looks like this piece, which would be the same thing as taking the the operator t times its adjoint and taking the square root. And then over here, this part here would correspond to taking an isometry. Okay, so this would be taking something that's an isometry, right? And so the isometry, right, something has to do with the identity, right? And over here, this is something on the unit vector, right? So that's kind of the connection there. So this right here, some of the properties of an isometry is that this matrix here is just simply a rotation and a scalar that preserves length. Okay, so you're preserving length, and then this part here is like scaling. Okay, so it's a positive operator. Right, so this is a positive operator, which kind of makes sense, right? Because in terms of scaling, you always want to, when you're doing this picture, you're never going to multiply by a negative number, right? So you're always kind of stretching the vector from the origin outwards. Okay, so this is, maybe this helps, maybe it doesn't, but this is kind of maybe this kind of back and forth here is kind of what kind of motivated kind of what this kind of decomposition. And it's the idea that, like, if we start thinking of these things as somehow having a mirror object inside of the complex numbers, if we can do something on the complex numbers, it might tell us that we can do something on the real, in the set of linear operators. Okay, so that's all I had for this part. We'll pause, and then in the next part, we're going to sketch out the proof for the polar decomposition theorem.